Good day. This is Professor Arnold, and today I will be explaining to you how to work problems involving the Poisson probability distributions. I will do that with a couple of examples. So, first off, what is a Poisson probability distribution? It is a discrete probability distribution that applies over a specified interval. The random variable x is the number of occurrences of the event in an interval, usually the average. The interval can be time, distance, area, volume, or some single unit. Here are the requirements for the Poisson distribution. The random variable x is the number of occurrences of an event in some interval. The occurrences must be random. The occurrences must be independent of one another. The occurrences must be uniformly distributed over the interval in use. So let's talk about the parameters and properties of the Poisson distribution. The mean is denoted by mu, usually, and the standard deviation is sigma, and that's equal to the square root of mu. Now, we would not need this information for the problems that we're going to be doing today, but in later chapters, we will need that information. So you might want to make a note of it. So, continuing with the properties, a particular Poisson distribution is determined only by mu. So if I want to describe a Poisson distribution for you, all I have to do is say it's a Poisson distribution and the mean is mu. Another thing you need to know about the distribution is that it has possible values of 0, 1, 2, 3, and so on. There's no upper limit. In other words, it's finite. But the point here is to remember that it could be 0. It doesn't have to be just 1, 2, 3, 4. It could also be 0. So let's talk about notation. I said a minute ago that the Poisson distribution may be denoted by the word Poisson followed by open parentheses and whatever the mean is. So let's talk about the formula. The formula for determining the probability of the event occurring x times over an interval is given by the following. We have the probability of big X is the variable equal to a specific number, 5, 6, 7, or whatever, is equal to E, and E is the irrational number approximated by 2.71828. So it's E raised to the minus mu. Mu is the mean given for the Poisson distribution. And again, we have mu multiplied by mu raised to the power x, and that whole quantity is divided by x factorial. Remember, x factorial means, for example, 5 factorial will be 5 times 4 times 3 times 2 times 1, just like that. So on the TI-83 or 84 calculator, we have an equivalent function, not formula, but function. But the function uses this formula, and it's called Poisson PDF. So if you use that function, like in any other function, you have to give it arguments or input values. And the input values for the Poisson PDF function are mu, the mean, and x, which is, you're trying to find the probability of the event occurring x number of times. So you will have to give it that value as well. So let's talk about another formula. And this time it's called Poisson CDF. And the Poisson CDF is used if you're trying to determine the probability of the event occurring less than or equal to x. Let me read that again. Occurring less than or equal to x times over the same interval. And the formula is the probability that big X is less than or equal to X is equal to Poisson CDF mu comma X. So now we're ready for an example. So the first example is assume that a Poisson distribution applies. That means we don't have to worry about checking the requirements. And that the mean number of hurricanes, so remember for Poisson probability we need a mean over some specified interval. So that mean in this case is 7. So it says 7 per year. So year is our time interval. So we have all the ingredients that we need here. We know that mu is 7. And the question is asking us to find the probability that in a year, the same as given in the explanation of the problem, there will be 5 hurricanes. So they're asking you to find the probability that in a given year, there will be 5 hurricanes. Also, in a 40-year period, how many years are expected to have 5 hurricanes? So let's go to solution number 1 for part A. We can do this manually. Manually here means that we're going to just substitute in the formula. So we need the two values, mu and x, and that we will just substitute into the formula. And the formula was e to the minus mu. So now it becomes e to the minus 7 mu, which is 7, raised to the 5th power, x is 5, and then the 5 is in the denominator. So this gives us e to the minus 7, 7 to the 5 over 120, because 5 factorial is 120. So I put that in the calculator, and I get 0.12771. Now I have 5 places here because usually in probability questions, they usually need the answer to 4 places of decimal, which means that we have to work in 4 throughout the problem. In this case, it's just one instance. So we have to round this 0.12771 to 4 places, and that will give us 0.1277. So the other way to do this is to use the calculator that we said. And I want you to notice that we're going to use the function PDF right here. You see the P? I'm highlighting it right there. PDF. And the way you find that on the calculator is to select second var. So let me show you the calculator. Here's the calculator. And you see your second key is right here. And then the var is right here. Okay. So you press those and then you'll get this right here. Is this list of functions. And then you choose Poisson PDF in this particular instance. So we put that in there, and see the calculator again, and at the top you see what the function looks like. You see Poisson PDF with the values substituted, and we get that big long answer 0.127716. So all we need is 4 places. So we're going to round this to 0.1277, the same answer that we got when we did it manually. So we need to continue to the second part of the problem. And in this problem they ask you, in a 40-year period, how many years are expected to have 5 hurricanes? So here it could be done manually, and all we need to do is multiply the value that we received in number A by 40. It's as simple as that. So I just reiterated how we got the value, but you don't have to. You can just pick the value from what you had before. So it's 40 multiplied by that e to the negative 7, 7 to the 5 over the 5 factorial. And this time we get 5.1 years, and depending on how many places of decimal they ask you for, so usually if it's years, it's going to be, to the nearest month or something like that. So 1 place of decimal would suffice. So the answer in this case is 5.1 years to 1 place of decimal. If they had asked you to the nearest year, it would be 5.0 years. Now let's go on to problem number 2. In a recent year, a hospital had 4,200 births. Find A, the mean number of births per day, then B, use that result and the Poisson distribution to find the probability that in a day there are more than 15 births. Now, find the mean number of births. All that means is to take the total number, which is 4,200, and divide by the number of days in a year, which is 365. So that gives us 11.050685. Now I'm using 5 places here because for the second part of the problem, we're going to need to give the answer to 4 places. So we need to start off with using more places of decimal, typically 5. So just to conclude this question, and this probably is going to ask you for the answer to the nearest 1 place of decimal. So the mean number of birth will be 11.5. But don't forget, you have to keep that value, the big long value, 11.50684, for use in the second part of the problem. So let's go on to that second part. So that part says, use the result and the Poisson distribution to find the probability that in a day there are more than 15 births. Now, more than 15 does not include 15. The other thing is we cannot use the probability CDF straight up because that gives you less than or equal to. But we can use some knowledge about probability to reformat the solution so that we can use Poisson CDF. So what we do is we translate the probability of x greater than 15 to a form that we can use the Poisson CDF, and that is the probability of x greater than 15 is equal to 1 minus the probability of x less than or equal to 15. Now we can use the Poisson CDF because we have a case of probability of x less than or equal to a number. So that's going to give me 1 minus Poisson CDF 11.50684, comma 15. And we put that in the calculator and we get 0.1221. So that brings us to the end of this presentation. I hope you understood everything that I explained. If not, you can play it again, pause it, stop it, use your calculator, check the values that I have put in, and so on. Thanks for watching, and I'll see you again in another video.